Okay, so there seemed to be a question about this 1D representation, or I should rather call it 1D example. So, of course, in reality, it's 3D, right? So that's how that really is. So the brain is in there, and then the reason I chose a 1D example is because it's much easier to draw. So so if you would draw a 3D realization of a random field here, this whole thing would be filled with colors, right? And the colors represent the height of the statistics. So if you think you go from yellow to red, then or from let's say that's a typical thing, you go from yellow to red, then you have everywhere some color in this 3D thing. If you, and that's easier to draw if you go to 2D and you look at a given slice. So let's say look at a slice, so maybe not at the edge. So we look at that slice and we look at a realization of the random field, then we get something that, this is something that you might sometimes see in a 2D representation. You get this, and then you have a surface of things going up and down in 3D. Yeah, so you have this kind of surface. And here the voxels, of course, would be two-dimensional coordinates, so they would be these things. Here the voxels are these 3D points in space, and then so that's 2D. And then what I, just to make this easy for visualization, is that I assumed the brain is one-dimensional. So I didn't reorder all the voxels in 1D, but I just assumed that the brain is one-dimensional, so just oriented along a line. And then a realization of a random field takes this thing, and the voxels are here. And here, of course, the coordinates, and we will get to that now, are three-dimensional vectors. If you look at a 2D random field, the coordinates are two-dimensional things, and here the coordinates are one-dimensional things. In this case, if you have a random field with a one-dimensional coordinate, this is also called a random process. And the Gaussian processes are an example for that. But of course, a random process is a random field. It's just a special random field where the parameter is just, or the coordinate is just one-dimensional. Yeah, but there was no reordering of voxels or anything. It was just to make the drawing easier. Yeah. Good. Any other questions about the last hour? No. Good. So then, having established kind of the conceptual ideas, we now want to go in and understand more how these p-values are actually computed, because this was so far a nice story in terms of intuition, but of course in the end you have a number in the table, and the question is how does the intuition relate to that number? And to do that, we will have to discuss a number of things. The first thing is to discuss what we actually mean by a real valued random field, so that we know the basic entity that we are dealing with. So that's the first thing, and some aspects of that. Then we have to discuss Gaussian and Gaussian related random fields, because these are the random fields that we actually deal with in brain imaging. So they are special random fields. And then we have to already discuss how to measure volumes. And once we've, so this is kind of background theory. Once we've done this, then we can get closer to the brain imaging random field story, where we then introduce things like smoothness. So this will be a big thing, smoothness, and we can only introduce smoothness once we talked about volumes, because we need this Resel notion, and we need things like excursion sets and reasons. So that will be the first application, and then we talk about excursion set features and their distributions, and then we are almost there. So then the last bit is essentially the SPM table. So we will not, because time until the end of the term will not allow, discuss in detail how the estimation works. So obviously I wrote all of this up. So we have this preprint on the p-values in SPM, or however it's called. It changes its title sometimes because what was it called? I think it was called Random Field Theory Based P-Values, a review of the SPM implementation. Let's see whether it stays like that. But so this is a rather long manuscript, which is also basically forming most of the stuff that you have in your script, and it also discusses the estimation, and we will leave estimation definitely out. I think we will also leave out the set level inference, just because of the time constraints. But there is this entire document, and I'm currently revising that for the reviewers. Anyway, you can learn more about that. But this is, I think, the plan for the remaining 5 hours then. Yeah? Good. Then let's start today with real valued random fields. So if you want to introduce random fields or real valued random fields from a very mathematical and grounded perspective, you would have to be familiar with the standard model of probability theory involving probability spaces and random variables as mappings. This we didn't do, and you may or may not be familiar with that. So I'm talking about the measure theoretic foundations of probability theory. They are, however, also not completely crucial to have a good formal and intuitive definition of a random field. So if you are not happy with the notion of a probability space, but are happy with this general or more intuitive notion of a random variable as something that takes on random values, then you're fine. So it also works that way. So let's define what we mean by real valued random field. So a real valued random field, and this is mainly about establishing notation. X for which X in S on domain S subset RD is a set of random variables This means each x at location x is a random variable, and x r d to r, x maps to xx is a function. Yeah, so what this just should capture is, again, if our d is 1, so if we are in the one-dimensional case, then our random field can be viewed, and this is the important thing, so you can view this in two things. So you can view this as a function, as a random function. Maybe we should put this in there, random function. So you can view this big X as mapping each small x to a value xx. So this is x, here's the small x. And like for any function, x allocates to small x a value, and then you can draw the function. At the same time, each at each location x here, each xx has a distribution, and it's a random variable. Yeah. So if one does this a little bit more formal, and that, which is actually easier, so based on a measure theoretic framework, x actually depends on two things. It depends on the outcome of a probability experiment and on space. So this is the omega you can view as the Zufall? What's Zufall in English? Yeah, exactly, but that doesn't really work. Anyway, so this is what Zufall does. Yeah, what the randomness does, and this is what space does. But this dependency is usually neglected, and then it's just considered to be a function of space, as you can see here. But by appreciating that each of these values at location, so for each of the small x, is a random variable. Yeah? So they are, if you want, they are special functions. So you can, yeah, it depends on how you want to view it. So you can think that you sample at each location because they are all random variables. And this is the important thing, these random variables have certain covariance properties. And because of these covariance properties, you get these things that there is some spatial covariation. If the covariation between neighboring random variables is completely zero, then it's called a white noise process, and you get something that you would maybe feel more is like a real random variable, that you get something like this, so that it's at each location it can happen whatever, But if you have these spatial dependencies, or these dependencies over the parameter, then things look more like functions. And if you get new realizations, and we've seen that already, then you get a different function. So you can view this also as functions. A different way to view it, and this will also be related to when we talk about Gaussian processes, is to think in terms of multivariate Gaussians, for example, or vectors, and then think of a vector as a function. Yeah? So if you have a random variable, now let's call this here x at location x, and this is distributed according, no, that doesn't make sense, sorry. If you have a random vector x, that is distributed according to a multivariate normal distribution centered at 0 and with a given covariance matrix. And you get this vector. This vector is n-dimensional. And you plot this vector as a function. So you plot the entries of x over space or over some coordinate, time, space, whatever. Then you can also view this as a realization of a random field. Yeah? So you can view random fields and random processes as generalizations of random vectors. These are these very different views, or 3 different views on random fields. The important thing is that if you obtain a given realization of a random field, you get something as a function over space, because there are, and this is the important thing, there are infinitely many random variables. Yeah? So questions about random fields of this definition. I think it gets a little bit easier once we talk about Gaussian random fields, because then you also see how you can create them. So no questions right now. What one needs to further specify, or what one can use to further specify random fields are expectation, covariance, and variance functions. So if we have a real valued random field, so for x, which is the standard way now to write this, S is the domain of the random field, so a subset usually in brain imaging of R3, and will also be later often called the search space, because this is just the space over which the random field extends. So for a random field, the expectation function is defined as follows: M from S to R. So remember also here the values that the random field takes on are always real numbers. And we can also emphasize that here. So this is why this whole thing is a real valued random field. You can of course also imagine vector valued random fields, so that for each location in space you allocate a vector. But here the values that the random field takes on are always scalars. So our mean function then also takes on a scalar or expectation function, and at location mx, the expected value, so the average over many observations, is the value of the mean function. Yeah. So the way you can view this, again from a intuitive point in 1D, is that there is a function. For example, let's assume a sine function in this case, roughly, that corresponds to the mean. So that's mx. And in addition to that, you have, of course, variability at each location in space. What we've already established, and this is what the mean or expectation function will do for us, is that we assume that the expectation function for our null model in random field theory-based p-value evaluation is always 0. Yeah. So for random field based p-value evaluation, fMRI, whatever, this expectation function is 0. Yeah? So that's also corresponding to the null hypothesis. But that doesn't have to be the case, of course, in general in random field theory. Then there's something called the covariance function. And that is specified for always pairs of locations, x and y. So, for example, here x and here y. And allocates to each of these pairs the value of the covariance function, which is just the covariance of the random variable located at x and the random variable located at y. Yeah. So this, of course, you can always view covariance as the covariation or the correlation that you get from many observations. If you have positive covariation between these two locations x and y, this would mean that when you sample something positive for x, you have a high probability to also sample something positive for y. Or if you have positive covariation, if you sample something negative from x, you also have a high probability to sample something negative for y. If you have negative covariation between x and y, then whenever you sample something positive from x, you have a high probability to also sample something negative from y, so crossing the zero essentially. And if you have no covariation between x and y, then regardless of what you sample at x, you sample something at y. So that's talks about in this case then, if we talk about space, the spatial covariation. Of course, if the spatial covariation here depends on both x and y. No? And if you, for example, have another thing here z, then what we will see later is that the covariation of random variables making up this random fields depends on the distance. So x will be covering more with y than it will do with z, because z is further away. So this is where this spatial covariation comes in, which is of course closely related to this idea of smoothness. So if you have something smooth, then you have correlation that is strong over wide part of space, while if you have something that is rough, there's hardly any covariation over space. And it would be nice if things would be simply specified in terms of covariance functions, and this would be our description of smoothness, but it's not, and this has to do with how brain imaging evolved. But this is the crucial parameter, or the crucial property of a random field that can encode things like smoothness. No? Although its parameter is slightly different in brain imaging. And then there's the variance function. Yeah.
Concerning the dimensions, x and y are still part of the space, of the three-dimensional space, right?
Yeah, so I will always draw them in 1D, but the x, y is always something d-dimensional, and for the brain, this is always three-dimensional. Yeah. So the variance function is defined as the covariation with itself, like the variance is defined. That's of course always larger or equal to 0. and this mainly will play a role for the definition of Z fields, because Z fields or Z random variables have the probability that they have a variance of 1, and Z fields will have the probability that the variance function is 1 everywhere. And this is just defined in terms of the covariance function. Yeah, so the expectation function important because it will encode the null hypothesis, the covariance function important because it can encode smoothness, and variance function because we sometimes need it for Z fields. That was a question.
Is this the definition of a potential random field of voxels x and y? Two voxels x and y, or what do the x and y mean here?
So S is a subset of 3D space, yeah. And if you now think, if you have 3D space, then each voxel corresponds to a three-dimensional vector because it's a three-dimensional location space. And for all of the voxels, this function, the covariance function. So if you take two arbitrary voxels x and y, it gives you the covariance between the location between the random variables located at a location x and at a location y.
Okay, so x and y are not two voxels, but refer to the locations of potential voxels.
Okay, so I think what you are maybe then referring to is about the discretization versus the continuous version. So, and I haven't really stressed that a lot. So the random field theory and this random field definition here, of course, doesn't talk about voxels. So it talks about continuous 3D space. And voxels are samples of this 3D space, or 1D or 2D if I draw things. So a voxel is, and this is also important, so a voxel is not kind of a cube, something like this, but a voxel is a point in 3D in this logic. So we have, so everything is, of course, all these locations are three-dimensional coordinates, and then we describe how this random field happens in 3D space, or how it behaves in 3D space, and we sample it at specific points in 3D space, and these are called voxels. And this is also important. So there are two things to this. One thing is that it feels a little bit like we are modeling a little bit too much because we only have data at the voxels, so why are we modeling everything that is in between voxels? Yeah, the other thing is voxels are not real, right? Voxels are just the locations where we sample reality, and reality, depending on who you ask, is a continuous thing, or it's definitely better described. So I think the brain is definitely better described by being formed by continuous 3D objects than as a voxel object, because if you cut out the brain, you don't see any voxels. It's not like that you can then dissolve into voxels. So the voxels in this scenario are the locations where you sample the random field. This is always also called a lattice approximation to the random field.
Okay. Yeah, but I'm trying to understand how this expectation or covariance functions compare to covariance and expectation parameters of normal vectors.
Normal vectors? Why normal vectors?
I mean, real valued vectors. Because here we have covariance function and a variance function, and we have x and y. And, x and y.
So these are real values. So this is a scalar. Mm-hmm. Yeah?
Okay.
So it's not that we compute covariances of vectors here. One can also do that, but this is not what's happening here. We have two random variables that have that take on real values, and one random variable is x at location x, and one random variable is x at location y. So we have two random variables that just take on scalar values.
Okay.
And
the random variables are potential voxels?
Yeah, I don't know what you mean by potential voxels. They are random variables that are located in space, or they are random variables that make up this random field. And yes, it can be that at this location x you actually sample, and at with the fMRI machine, and at this location y you sample with the fMRI machine. Of course. So in this sense, they are potential voxels. If that's what you mean by potential voxel.
Yeah, I mean potential voxel in the sense that one of many voxels that we could sample voxel.
Yeah, I mean these are just all. I think the better way to think about x and y, so the small x and y here, is just these are all pairs of spatial locations in a 3D volume. Okay. So you can so you have a 3D volume, and then you can choose one location here, and then you choose another location here, and then the covariance functions gives you the covariation between the random variable at this location and at this location.
And they're always three-dimensional vectors.
I don't know what you mean by three-dimensional vectors. So what are three-dimensional vectors?
Or, I mean, R3 values.
Like this here or this here?
Underneath the null hypothesis. Right. Yeah.
This here.
Yeah.
Of course, a 3D location is encoded by So I think you have to differentiate between. So let's do it for y. So y is three-dimensional because that's a location in space. So that's has a y x, a y y, and a y z number. Yeah, and x of y is a real number because that's just the value that is allocated to that 3D location. Yeah. So it's also called in physics, these are called scalar fields. And so you can also view these kind of as random scalar fields if you want, as opposed to random vector fields. Because we could have also at each 3D location, we could have a vector, but we don't, we have a scalar. Yeah? Good. Yeah, so these are these basic descriptors of random fields that we will need. And another thing that we will often encounter is stationarity. And the important thing that we require here also to make things or to relate things or to give an example later on is wide sense stationarity. And I actually already mentioned what I mean by this. This is the property of the covariance function of a random field to only depend on the differences between two locations and not on the absolute locations. So x, so a random field is wide sense stationary if first of all the mean function is constant, or the expectation function. I always say mean because it has an n. For ORM bar here being a real number, which means in 1D, of course, that the mean function is just constant, like this. And of course, we already established that we are mainly interested in the case that the mean function is actually 0, because that corresponds to our null hypothesis, that there is no activation at all. And the other thing is that the covariance function depends only on the difference between two locations, so that our covariance function C is only a function now not of tuples of locations, but only of a given distance in space. And this distance, of course, is also a part of the search space. So if it's in 3D, it's a 3D distance. And this distance encodes the covariance, and D is our distance x minus y. So the point here is that in principle it's completely possible that if you have x1 and y1 and x2 and y2, that x1 and y1 have, for example, a strong positive covariation. So whenever you have something sampled positively at x1, you also sample something positively at y1, and that x2 and y2 have a complete negative covariation. They are just different locations, and the covariance function just allocates covariation to any 2 points in space. Now, this wide sense stationarity says whenever 2 points have the same distance from each other, they have the same covariation, because the covariation is just a function of distance. And now, in this case, the distance here between x1 and y1 and x2 and y2 is the same, so they also have the same covariation. Which also means that, in a way, the covariance doesn't change over space. It changes based on the distance. So if you fix some point in space here, and you go to this distance or to this distance, then the covariance will usually actually decrease. So things that are close together in space have high covariance, and as you go away from one location, the covariance will decrease. So something that's, if you have sampled something positive in the front of the brain, this will not influence much what you sample in the back of the brain, but it will influence other things that you sample in the frontal cortex, if you want. But it's independent of space in the sense that this kind of decreasing covariation is the same if you take another reference point. So if this was your first reference point and here you have another reference point, how this reference point relates to other things is the same. Yeah, so this is wide sense stationarity, and this is also called, if you have stationary random fields, homogeneous random fields. Homogeneous random field, and it's a typical assumption in the probabilistic theory then about random fields. So essentially the computations to evaluate certain probabilities get easier if you make this assumption. So if you assume that the covariation between 2 locations only depends on their distance, but not on their absolute location in space. Yeah. I think I have a picture of that. Yeah. Let's have a look at this picture and then also stop here. So we haven't really introduced Gaussian random field yet, but we will do so then next time. but it doesn't matter, so you can just view this as any random field here. So this is the visualization. So what you see here is plotted the covariation as a distance function. So 0 is any location in the random field, and this plots the covariance as you go away from this location for different parameters. Yeah? So you can have for this bluish thing, you can have relatively high covariation still at 0.3 distance. For this red one, I think it's red, right? For this red one, you have already quite small covariance already at 0.1. Now, if you create realizations of random fields, in this case Gaussian random fields, but that doesn't really matter, it's independent of whether it's a Gaussian or some other random field. If you have this, if you have relatively little covariation at short distances, then you will of course observe more variation over space. It will look more like this. So this is this L0.1 here. If you have strong covariation over space, then of course you will have more. You will have far less variability over space, higher smoothness. Yeah, so that's kind of one way you can think about it. It's not the smoothness parameter relation that we will later see, but it's fairly related to it. So if you have if your covariation over space drops quickly, then the realizations will become rougher. If your covariation drops very slowly over space, then the covariation will remain over space quite strong, and you will have more smooth realizations. Yeah. Good. Questions? You don't look convinced, but maybe think a little bit about it, and then we can discuss that next time. Yeah, so then next time we will introduce Gaussian random fields as a special and important case of random fields that we need, and then continue with our explorations into random field theory. Good, then see you next Monday.